Hello everyone. Today we will discuss some problems related to week 6. So in week 6 we have studied about ferromagnetism, correlation, mean field theory and theory of specific heat and the solids. In that uh, theory of specific heat of solid, we have studied about device and Einstein's model of solids. So we'll do some problems regarding this device theory. So the first question is the device temperature of diamond is given 2230 Kelvin. Then calculate the highest possible vibrational frequency and molecular specific heat capacity of diamond at 10 Kelvin. So what is given? This Debye temperature, let's denote it as TD. It's given as 2230 Kelvin. We have to calculate the highest possible frequency of vibrational. We have to find nu, which is hello. So I just started. This is the first question. So I'll say again. Okay, so in last week's class we have studied, Sir has taught, in week 6 Sir has taught about ferromagnetism, correlation and mean field theory and theory of specific heat of solids. So from that specific heat chapter we have studied Debye's model and Einstein's model of solid. So first I am going to do some problems regarding this Debye's model. So in this first question, it is given that Debye's temperature of diamond is given at 2230 Kelvin. Then we have to calculate the highest possible vibrational frequency and then the molecular specific heat capacity of diamond at 10 Kelvin. So let's denote this device temperature as TD, which is given as 2230 Kelvin. Right. So in class we have seen one form of device as HCS, I think. Yeah, HCS over 2 6m divided by 5p or 1/3. So it's given here where this CS is the velocity of sound in that solid. Here it is given in terms of sound, but we will use some different formula. We will approach it directly. So I will give you some different formula for this in terms of frequency, which will be h nu over kp. So here this is Planck's constant, this is Boltzmann constant. So we will put this values directly and we can find the highest frequency. Let's denote as nu h. This is nu h. So we have all these values. We will find this nu h as TD Kb divided by H. So this will be TD is 2230 Kelvin. Then Kb's value is Boltzmann constant. It is around 1.38 into 10 to the power minus 23. Its unit is meter square kg per second square per Kelvin. This unit is Kelvin. Then we need Planck's constant. Planck's constant is 6.63 into 10 to the minus 34 meter square kg per second inverse. So you see, Kelvin cancels, kg cancels, meter square cancels. So we are getting in terms of second inverse or Hertz. So we just have to calculate this. Okay, I don't have. If you have calculator, can you tell me this value? Highest frequency. So around 4.64 into 10 to the power 11. So this is the highest frequency of vibration. Means what happens in solid, as we give some temperature to the solid, there are some molecules in the solid. So as we provide heat to the solid, they will start vibrating around their mean position, right? So if they are vibrating, they have some specific frequency of vibration. So we have calculated that highest possible frequency of vibration, right? Then so depending on the highest frequency of vibration, their capacity of carrying heat will be different. So we can calculate the specific heat for that case also. And in class, as you may be remembering, in low temperature we have calculated specific heat formula, which was like 12 by 5 to the power 4 T over T to the power, that is not to the power, okay, this one. So we have direct formula and we know the TD value. No, actually we are set to calculate at 10 Kelvin. So we have TD value and T value is given at this 10 Kelvin. Then we can put this and we can find this value. T is 10 Kelvin, TD is 2230 Kelvin. So if you calculate this, you will get around 1.75 into 10 to the power minus 4 joule per mole per Kelvin, right? You just verify putting all these numbers how much you are getting. There is some there's some other constants also we didn't do. This formula was given in class, so it won't be 1.75, it will be something different, but in exact formula there should be some other constant uh, so don't bother about this. Whatever value we are getting, that's also correct. Okay. Did you understand this question answer?
Can you explain the second part?
Okay. First part we calculated the maximum frequency, right? Then in second part we are asked to calculate the molar specific heat capacity of that material at temperature 10 Kelvin. So as you might be remembering from class, we have in week 6 class, sir has derived some specific heat formula like this: 12 by 5, 5 to the 4, T over TD. This is for lower temperature. Lower temperature in the sense this temperature should be less than TD. This T less than TD. So in that condition, this specific heat formula is this one, right? So we are asked to calculate the specific heat at 10 Kelvin. So we are given this temperature value, and previously we are given this device temperature, which is TD, which is 2230 Kelvin. We are given this value also. So all values we have. So putting all these values, you should get something like this. So from this you might be wondering, these are all dimensionless, how am I getting this joule per mole per Kelvin? Because sir has taken all the other constants as one, that's why. So if you want to do uh, like in SI unit, then you might have to multiply one constant which consists of other constants kb or some other constant which contains this um, units. So for simplicity I didn't consider this constant, so if you calculate this, it won't be 1.75, it will be some other value. uh, if you put this constant, which I am not deriving, its constant value will be some 8.31. If you put this 8.31, then you will get this 1.75 value, right? You try this. I have given you R value also, so you put all the values, then you will get 1.75 in 10 to the minus 4.
Okay.
Okay. So coming to the second question. For copper, the lattice specific heat at low temperature has behavior. Uh, this specific heat behavior is given as TQ, and some constant is given. So we have to estimate the divide temperature for copper. So Cv is given as 4.6 into 10 to the minus 2 TQ kilomole inverse, mole inverse, Kelvin inverse, right? So we are given specific heat value, then we have to calculate TD, right? So in the previous question we have seen this relation Cp equal to 12 over 5 pi to the power 4. Let's write the constant again, this time this R, and this is T over TD, where this T is the okay, so I have written formula wrong here. So this will be Q, this is Q, okay. So here this will be Q. So we have everything. Pi value we know, R value is around 8.31. Actually this R consists of this number of particles. Somehow it's contributing around this 8.31, so I am not going to that details. Okay, R value is given 8.31 and this unit is uh, mole per Kelvin, uh, kilomole per Kelvin. Okay, so we are asked the value of TD, right? So what I can do, I can rewrite the CV value is given, all the other values are given. I need to find this TD. So TD cube will be 12 over 5 I to the 4 R T cube over CV. Right, I just taken this TD to the right hand side and I have taken this CV here, right? So this TD cube will be 12 over 5 I to the 4 R, this is T cube, and in the denominator we have 4.6 into 10 power minus 2 T cube, and we have kilomole inverse, so we need to multiply 10 to the minus 3 to convert it mole inverse per Kelvin, right? So you see we have T cube in the denominator and T cube in the numerator, so you can cancel them, and then we will have TD cube which will be 12 over 5 to the 4 R, and this is 1 over 4.6, and this is 10 to the minus 5 in the denominator, so in the numerator it will be 10 to the power 5. So after putting all this value, let's do this. Do you have a scientific calculator?
The same time, sir.
Okay. This is 8.3. This is around 4.21. Correct me if I am wrong. Then this TD value will be 4.21 10 to the power 7 cube. Just put this value and find this TD value. Maybe it's around 7.4. Maybe I'm wrong. Just calculate and verify, right? I don't have a scientific calculator today, so the idea is this, right? You understood the idea, right? Okay, we are moving to the next question then. So in the next question we have to calculate the desired temperature of gold if its atomic weight is 197 and the density is 1.9 into 10 to the power 4 kilogram per meter cube, and the velocity of sound is given 2100 meter per second. Okay. So I will give you another formula so you can check this about device theory. You can find it from Wikipedia also. If you search device theory, then you can easily find it. So I have taken the frequency omega d q. This relation I have taken from there, which will be for this is for 3-dimension case. The frequency will be 6 pi square n over v vs q, where this vs is the velocity of sound inside the material, inside the solid, and this v is the volume, unit volume of that solid, right? So we have omega, so you might be knowing omega. I can write omega is angular frequency, so I can find the frequency from this angular frequency from the relation omega is 2 pi nu, right? This is the frequency where this omega is angular frequency, so I can substitute here this nu 2 pi nu, so it will be 2 pi nu to the power q equal to 6 pi square n over v s. So I can write this frequency is the highest frequency of vibration of the molecules inside the gold crystal, which will be 2 pi square n over we have 8 pi q v vs. This will be q, right? So we can cancel 3, this will be 4 pi square, pi q will cancel, so this will be around 3n over 4v pi vs3. So what are the unknowns here? This n, we can take it as Avogadro's number, as we are talking about atomic weight. Then we can calculate the volume from here, as the density is given. Density is given as 1.9 into 10 to the power 4 kg per meter cube. So density means mass per unit volume, right? So from here I can calculate V equal to m by rho, right? I need this V. I can calculate from this relation m by rho. M is this one and rho is this one. So V will be 197 over 1.9 into 10 to the power 4 kg is given, so I can convert it to gram, 10 to the power 3 gram per meter cube, right? Then if I put this value, let me write down this. nu HQ is 3n over 4 pi. This V value is 197 over 1.9 into 10 to the 4 into 10 to the 3 as Vs. This is Vs cube. This is Avogadro number. So let's put this. So what is the value of this Avogadro number?
6.6 into 10 raised to 23. 6023 into 10 raised to 23.
6.6 or 6.02?
022.
6.02 into 10 to the power 23 divided by 4 into 3.14 by 197. So the denominator we can take to the numerator. 10 to the power 7 into 1.9, and Vs value is given 2100 meter per second cube. Can you tell me this value?
And how does this 10 raised to 7 come?
You see, there were this density was given 1.9 into 10 to the 4 kg per meter cube. So kg I have converted to gram.
Okay.
So as this Avogadro number is related to per gram thing, so that's why I converted to this to gram. So there. So this will be 128.43 10 to the power 30 36. Are you getting this also? Just verify. Then this is new h cube. So for new h we have to take the cube root 2843 38 can do one thing. 128.43 enter 10 to the power 1. Okay, you need to find this value only. This is 5.04. Just verify. So highest frequency we got. What is the question? Estimate the dip by temperature. So frequency we got, then the dip by temperature relation we know. This is h nu h divided by kb. So h is 6.63, 10 to the power minus 34. New value we got 5.04 into 10 to the power 12 divided by kb is 1.38 into 10 to the power minus 23. So this value 6.63.
241.
How much?
241K.
Right. Okay. So I also did this. It was getting 240. Okay, then it's correct. Okay, so in the question it was given atomic weight and density of gold was given. Then the velocity of sound inside this gold material is given. So we were asked the device temperature, right? So from this relation and from this angular frequency relation, which I took from Wikipedia, we have a relation between this angular frequency of the vibration inside the gold, inside the any solid, which is related to sound velocity inside on that material. So we have this relation. From this relation we found a relation in terms of highest frequency. This is angular frequency, we converted it to frequency term, and for this n is we take as an Avogadro's number, and v is the volume that we have calculated from this atomic weight and density. Then we finally derived this highest frequency of vibration of the gold molecules inside the material. Then from that we calculated the device temperature for that gold material, right? Now moving on to the next question. So in the next question we are given, so at low temperature the specific heat of rock salt varies with temperature according to this device law, where this A for low temperature 12/5 we have seen, but here it is given as just A, and this A value is also given here, right? Then TD value is also given. Then we are asked how much heat is required to rise the temperature of 2 gram of rock salt from 10 to 50 K, right? So what is the definition of specific heat? The specific heat definition is the amount of heat required to raise the temperature of the material in of 1 degree and that's it. Okay, so the definition of specific heat is the amount of heat required to rise the temperature of that material through 1 degree per maybe you say per gram of that material. So the definition is the amount of heat required to raise the temperature of that material per gram is called specific heat of that material. So we can calculate from this then per temperature means per 1 degree means per temperature per gram. So some mass is given, right? So from here, so from this definition we can write this formula like this: the amount of heat required to rise the temperature of the material in through 1 degree per gram of that material. So from this relation we can find that the heat required as mCVT, right? But what we are asked, what is the temperature, what is the heat required to rise the temperature of 2 gram mole of rock from uh, 10 to 50 Kelvin. So this Cv I can write as Cv equal to dq power dt per mass, which is in grams, right? So in that manner I can write dq as m cv dt, right? Then q will be integration of mCv dt, where this temperature goes from 10 to 50 Kelvin. So here q is, m is a constant, I can take out. This is 10 to 50 Cv dt. So we are given Cv formula as this. This will be m integration of a t over td q dt from 10 to 50. This a value also given, but it's a constant, we can take this out, and td value is also given, and which is a constant, so we can take all the constants out. So we will be having m a over td cube integration of dq dt from 10 to 50, right? This will be ma over d cube. This integration is t to the 4 by 4 from 10 to 50. Now we have everything, we just have to put all the values. M is 2, a value is 464, 464, td value is 281 cube, and we have 1 by 4 from here, and we have 1 over 50 to the power 4 minus 10 to the power 4. Can you solve this and tell me the number?
$65.
65. Yeah, okay, that's the answer, right? So this is 65 calorie. So we we need 65 calorie of heat to raise the temperature of 2 gram mole of rock salt from 10 Kelvin to 50 Kelvin, right? So you understood the process, right? We were given specific heat in terms of temperature and device temperature, and all other values were given, this constant value, and device temperature was given. Then we were asked what is the heat we require to raise the temperature uh, from 10 to 50 Kelvin of 2 gram mole of rock salt. So from the definition of specific heat, uh, we have this form in terms of uh, heat and temperature, and from there we calculated the heat by integrating out in terms of temperature, right? Now let's move on to the next question. One second. So in this next question, we were given a question like, consider the Ising type model where this Hamiltonian is given like this, and this is periodic. This Sn plus 1 is equal to Sn, this is periodic. But now imagine that Si can take value 0 or 1 for I equal to 1 to 3 to n. So where this Si and Si plus 1, you can assume them as spin of the particle. So in Ising model, what we do, we choose a point, we choose a particle at a point I, then we consider the interaction with its nearest neighbor, where it is I plus 1 and this is I minus 1. So this J term represents the interaction strength of this interaction between Si and Si plus 1. So in this question, this system is considered as periodic. From this condition, we can say that this is periodic. That means this line is connected to the other end. That means where this is I and it ends, it starts somewhere, right? I equal to 1, and it, let's write this is I equal to 1, and the last particle is I equal to n. So you see, for any particle inside this line, they have two nearest neighbors, but at the end points they have only one nearest neighbor to the left for this system, and for this I equal to 1, it has only one nearest neighbor to the right. It doesn't have any nearest neighbor to the left, and it doesn't have any nearest neighbor to the right for this I equal to n. So these 2 points are very odd compared to the other points. So what was the solution taken? So we just joined this end to this end. So in that case, this I equal to 1's nearest neighbor will be I equal to n. So I equal to n plus 1 will be equal to this one, right? That means I equal to n ends here, and we joined it to this end. So this I equal to n plus 1 will be effectively 1. So it is periodic. So the Hamiltonian is given like this, then we are and then this S value can be 0 or 1. Let's assume it will be spin, this spin value can be 0 or 1. So then we are asked to show the matrix form for this system. So you might be remembering from the class we are given the Hamiltonian as this, then the partition function z is calculated as trace of e to the power uh, e to the power minus beta h, right? Then sir has taken some as like some different form of this what do you call this, e to the power minus beta h. Let's write it first, then trace of e to the power minus beta, and h is summation over minus j SISJ. This one, that is from I to. So you see there is a summation in the exponent. So the exponent summation means let's summation of some ai, let's say. So I can write is to be as e to the power a1 plus a2 plus delta dot an. So I can write this as e to the power a1 into e to the power a2 similarly e to the power an, or equivalently I can write it as product of e to the power ai, where I going from 1 to n, right? So in this case also I can write this as trace of product of e to the power I going from 1 to e to the power minus beta minus j is there, so plus j si plus 1, right? So again, trace means what? Trace of a matrix A. That means if I have a matrix A like 1 2 3 4 5 6 7 8 9, then trace of A is nothing but the summation of the diagonal elements, let's say denoted as aii. When they are equal, it will take the summation I going from 1 to 3. So here trace of this can be written as summation over some let's write it as some j notation, then I have product I 1 to n, then we get for beta j si, right? Then I can interchange, actually no need to interchange. So for simplicity we are just taking this as matrix. This is a product. So from class you might be remembering sir has taken as we are considering s equal to 0 or 1, we have to take this matrix as 2 cross 2, as two values are allowed. So if we have three values, then we will have 3 cross 3. If we have q choices, then we will have q cross q matrix form. So this e to for each e is worth this number, I can take this as a matrix T. So for n value, we will have T to the power n matrices. So for each value, we will have T of S1, S2, T of S2, S3, and so on up to T of n Sn S1, right? So effectively we can say Z equal to trace of e to the power this term, or trace of this T matrix to the power n, right? Just one second. I'm just reminding you from the class. You can just verify from the class. We had a Hamiltonian like minus 2j summation over I equal to 0 to n minus 1 si plus 1 minus h over 2 summation over I equal to 0 to n minus 1 si plus 1. So for this we could calculate the matrix elements as Tmn equal to e to the power 2 beta j mn plus beta h over 2 m plus n. Here what is mn? M and n are the values of Si. So in this question, what are the values of Si? 0 and 1. So the values of m and n will be 0 and 1, right? So for this Hamiltonian, we had this matrix element like this. So in our case, what is the Hamiltonian? Is equal to minus j summation of I equal to 0 to n minus 1 si plus 1. So for this case, what will be the matrix element Tmn? From this relation we can see that we don't have any h, so we can neglect this part, and we had 2 here, so that's why we got 2. Now we don't have 2 here, so what will be the matrix element? It will be e to the power beta j mn, right? Where this mn can take value 0 or 1, right? Then I know the matrix elements as this one, then I can form the matrix T matrix as, so what will be the first element? This is 1 1 element. So first I am taking this m value is starting from 0, right? M and n, they are starting from 0. So this will be 0 0 element, this will be 0 1 element, 1 0 element, 1 1 element, right? So you have to take m equal to 0, n equal to 0 here m equal to 0, n equal to 1, m equal to 1, n equal to 0 here, m equal to 1, n equal to 1 here. So let's put those values and we'll see what is happening. So m equal to 0, n equal to 0, this is e to the power 0, which will be 1. For the second case, m equal to 0, n equal to 1, that means also e to the power 0, which is 1. For this case, 1 0, that also 1. For the last case, m equal to 1, n equal to 1, so this will be e to the power beta t, sorry, j. So this is the t matrix for our case. Let's check the answers. You see, yeah, we have an answer here. So if you want to calculate the partition function, you just have to do what? You have to just take this t matrix and take the trace of this t to the power n. Then you will get the partition function, and from the partition function you can calculate the mean values and the entropy, etc. So you understood, right? So I just took this from class where we had a Hamiltonian like this in general. So for that, the matrix element, this s value where only this s can take two values, so we will have a matrix 2 cross 2 form. So if this s value can take q values, then we will have solution as q cross q matrices, right? So this is the matrix element for this general Hamiltonian. So for our case, our Hamiltonian is like this. So from this Hamiltonian we derived this matrix elements like this, and this matrix element, from this matrix element we can form this matrix. So finally we got this answer. Okay, then move on to the next question. Okay, so in this question we are said that let's assume this e to the power beta j as x, then find the eigenvalue of this transfer matrix. This T matrix is called transfer matrix, that we got the form of this T matrix as this one, 1 1 1 e to the power beta j. Now we are asked to consider e to the power beta j as x. So what will be the T matrix again? Then this will be 1 1 1 e to the power beta j is x now. Now we are asked to calculate the eigenvalue of this 2 cross 2 matrix in terms of x. So what will be the eigenvalue? This will be determinant of this 1 minus lambda 1 1 x minus lambda equal to 0. So this is 1 minus lambda x minus lambda minus 1 equal to 0, or this is x plus lambda square, then this is minus x plus 1 lambda minus 1 equal to 0. So effectively we will have lambda square minus x plus 1 lambda plus x minus 1 equal to 0. So we have a quadratic equation. Then we know the general solution for this. Lambda 1 lambda 2 will be minus b plus minus b square minus 4ac over 2a, right? So a is 1 here, a is 1, b is minus x plus 1, and c is x minus 1. So what will be the lambda 1 lambda 2? This will be minus of b, means it will be x plus 1, then plus minus under root this b square, then this is x plus 1 whole square, then minus 4ac A is 1, C is x minus 4, x minus 1, sorry. Then 2x, A is 1, so okay, we have to solve this square root and part also. So this is x plus 1 plus minus, this is x square plus 1 plus 2x minus 4x plus 4. And this is x plus minus the root, so x square, then we have minus 2x and plus 5, so yes, x plus 1 plus 2. So what is lambda 1? Lambda 1 is x plus 1 plus x square minus 2x plus 5 over 2, and lambda 2 simple, there is minus x plus 1 minus square root x square minus 2x plus 5 over 2. So these are the eigenvalues. Let's check. We have those, yeah, they have there. So this transfer matrix, we are assuming this e to the beta j as x, then we are calculating the eigenvalues for this transfer matrix. This very simple, I don't think I needed to explain it anymore. So let's move on to the next question. Okay, so for the above case, we are asked to calculate the canonical partition function for n very greater than 1. So we calculate the partition function as trace of this t to the power n, right? So this t to the power n trace means we are just adding the diagonal elements. If we have a matrix, some n cross n matrix, then trace of that matrix means adding the diagonal elements only. So effectively I can assume this as a diagonal matrix instead of this T matrix. Actually I can form a diagonal matrix from this T matrix. Like if a T matrix is given, I can form a model matrix from this T matrix, which will be consist of these eigenvectors of this T matrix, V1, V2. Then for calculating the diagonal matrix, I just have to multiply S T S inverse, right? So it's equal as taking trace of t to the power n is equal as taking trace of d to the power n, right? Where this d is a diagonal matrix formed from this T matrix, right? So in that case, this D matrix, what it will contain? It will contain the eigenvalues in the diagonal. So for our case, it is 2 cross 2, so it will contain lambda 1, lambda 2, and all other elements will be 0. So it's an interesting property of diagonal matrix. If you have d to d square, then the matrix will be lambda 1 square 0 0 lambda 2 square, right? If I have e to the power d, then the matrix will be e to the power lambda 1 0 0 e to the lambda 2 function. So I have d to the power n, right? Then in this case, what will be our matrix? This will be lambda 1 to the power n 0 0 lambda 2 to the power n, right? So trace means addition of the diagonal elements. So this will be lambda 1 to the power n plus lambda 2 to the power n, right? Now we are given as n is very greater than 1. Then we have two solutions as lambda 1, lambda 2. Let me write down lambda 1, lambda 2 as x plus 1 plus minus under root some values we have, then 2. So I can take lambda 1 as the plus part, x plus 1 plus this square root by 2, then lambda 2 will be x plus 1 minus the square root of this divided by 2. So you see, comparing these two eigenvalues, I can definitely say the first one will be greater than the second one because there is a plus before this root over. It's definitely lambda 1 is greater than lambda 2, right? Then in that case, if lambda 1 is greater than lambda 2, what will happen to lambda 1 to the power n and lambda 2 to the power n? You notice this n is very greater than 1. So in that case, lambda 1 to the power n will be very greater, very high value, where this lambda 2's value is smaller than lambda 1. So its value will increase, but not as lambda 1 to the power n is increasing. So in that case, from these two elements, I can definitely say this is lambda 1 to the power n is dominating. So I can simply write it as approximation of lambda 1 to the power n, right? So lambda 1, what is lambda 1 for our case? It is half x plus 1 plus square root of this factor. What is this factor? X square minus 2x plus 5, and this is whole to the power n. So this is my answer. This partition function is this one. Understood? Hello? Any doubt is there for this question? Okay, let me tell you once more. Okay, we are asked to calculate the partition function for the above case. So from the above case we got two eigenvalues, and for calculating the partition function we have a formula like this, or we can write e trace of e to the power minus beta h, which we are effectively writing as in terms of matrix as t to trace of t to the power n. Right. So this T is general 2 cross 2 matrix, which will have non-diagonal values also. But I don't care about non-diagonal values. I am taking the trace, so I'll care about only the diagonal values. So you just diagonal values means the eigenvalue in 2 cross 2 matrix. Normally the sum of these diagonal elements will be the sum of the eigenvalues. So as I am taking trace, it doesn't matter if I change this T matrix as the diagonal matrix, which is formed from that T matrix. Just as I am just adding the diagonal elements. So if it is x1, this is x2, x3, x4. Trace of this, let's assume this is A, then trace of A will be x1 plus x2, right? Then this will be equal to lambda 1 plus lambda 2. That means sum of the eigenvalues will be equal to sum of the diagonal values of that matrix. So effectively I am changing this T matrix to D matrix. D matrix means this is diagonal matrix. So this diagonal matrix will contain the eigenvalues in diagonal part So the interesting property of diagonal matrix is that if I do any operation on this diagonal matrix, it will go easily. Like if I take e to the power d, then this matrix form will be e to the power lambda 1, e to the power lambda 2, and other parts will be 0. Similarly, if I take d to the power n, this will be lambda 1 to the power n and lambda 2 to the power t, and lambda 2 to the power n. So I am taking trace of this dn, right? Then trace means addition of the diagonal elements. So I took this addition of the diagonal elements. Next, we are given as n is very greater than 1. So n is very large number. So we calculated lambda 1, lambda 2, and from this expression we can definitely say this lambda 1 is greater than lambda 2. So in that case, lambda 1 to the power n will be very greater than lambda 2 to the power n. So I am writing this z equivalently lambda 1 to the power n. Then I am putting this lambda 1's value, and we are getting this answer. Which one? This one. Yeah. Okay. Then moving on to the next question. Okay. So now the next question says, now in the above model, add a magnetic field so that the Hamiltonian becomes like this. So previously we had a Hamiltonian like this. Now we are adding a magnetic field small h. So this Hamiltonian changes to like this. Then find the transfer matrix and find the eigenvalues of the transfer matrix. Then find the canonical partition function. So similar to the previous case, we just have to find the T matrix first, then the process is same. So from the class we had a general for a general Hamiltonian like minus 2j summation over si plus 1 plus 2j 2h summation over j equal to 1 to n, sorry, I equal to 1 to n, I equal to 1 to n, si plus sj. We had the matrix element Tmn as e to the power 2 beta j mn plus beta h over 2 m plus n. Right. This I took from the class, from Sir's class. So now we have a Hamiltonian like here we have minus j summation over j equal to 1 to n si plus 1 plus h summation over si sj, okay, sj plus 1, then j going from 1 to n, right. So then I am comparing these two Hamiltonians. I need a addition term here so that I can get a general formula like m plus n. So I can rewrite the second term as h over 2 summation over j sj plus sj plus 1. I am just rewriting this term as this one, right? Then I have to compare. So they have 2j here, so that's why 2 is coming. So for our case there is no 2 in the first term, so our Tmn will be e to the power just simply beta j m n, right? Then for the second case, maybe this is not 2h, let me confirm. So this is h by 2, sorry, this is h by 2. So for h by 2 we have beta h by 2 m plus n. So for our case also we are having h by 2, then I can take this value as m and this is n, this is n. Then for this case h over beta h over 2 m plus n. So for this Hamiltonian we are getting a matrix element like this, and as the first question states, this SI can be 0, 0 or 1. That means m and n value should be 0 or 1. Now I have to form the matrix. So this T matrix will be consist of 0 0 0 1 1 0 1 1 element. So this is the first one is m value, second one is n value, right? So putting these values, m equal to 0, n equal to 0, in this first case we will have this is 0, this is also 0, so we will have e to the 0 which is 1. So the second case 0 1, so m equal to 0, n equal to 1. So first term this one is 0, but here you see if m is 0, n is still 1, so we will have some terms here which will be e to the power beta h over 2, right? So coming to the third element here, m is 1, n is 0, so m is 1, n is 0, so this is 0. Here you will have e to the power beta h over 2, and for the last element we have 1 1. So m equal to 1, n equal to 1, so this will survive. M equal to 1, n equal to 1, this will be 2, 2 will cancel, so we will have e to the power beta j plus beta h. This is m equal to 1, n equal to 1, yes, multiplied by 2. So this is the T matrix, right? Now what do we have to do? We have to find the eigenvalues, then we have to find the canonical partition function. So eigenvalue calculation process is same, just let's take this e to the power beta h over 2 h x beta h over 2 x, okay. Then what is the beta h over 2, it will be ln x, then beta h is 2 ln x or ln x square. So beta h is ln x square. So what will be e to the power beta h? This will be e to the power ln x square, which is x square, right? So e to the power beta h is x square, e to the power beta h over 2 is x. Now we have beta j. Let's take e to the power beta j as y. So this term will be y into x square. So let's rewrite in terms of x and y. This T matrix I can write as 1 I have e to the beta h over 2, that means x, here also x, here I have y into x square. This is my T matrix. Now I have to calculate the eigenvalues. So determinant of this 1 minus lambda x x y x square minus lambda, this is 0. So what is the expression I will have? 1 minus lambda y x square minus lambda minus x square equal to 0. This will be y x square plus lambda square, then minus yx square plus 1 lambda minus x square equals 0. This is lambda square minus yx square plus 1 lambda. So I have what I have y plus 1 x square equal to 0. So I got this quadratic form in terms of lambda. Then I can find lambda 1 lambda 2 as from this equation minus b plus minus b square minus 4ac divided by 2. Right. My b is minus yx square plus 1, a is 1, c is y plus 1 x square. So putting these values, I will have yx square plus 1 plus or minus the root this yx square plus 1 whole square minus 4 x square y plus 1 divided by 2. So I got the eigenvalues lambda 1 lambda 2. From these I will take lambda 1 as the plus 1 in this part plus the root over divided by 2, and lambda 2 will be the minus part, minus root over of this divided by 2. So clearly the lambda 1 is greater than lambda 2, right? So to calculate the partition function z, it will be trace of t to the power n, which I can effectively write as trace of the diagonal matrix to the power n, or explicitly I can write it as lambda 1 to the power n plus lambda 2 to the power n. So you can see, as for n is very greater than 1, this part will dominate, as this lambda 1 is greater than lambda 2. So this effectively I can write it as lambda 1 to the power n. So effectively my partition function will be z equal to yx square plus 1 plus square root of this yx square plus 1 minus 4x square y plus 1 divided by 2 whole to the power n. You substitute the values of y and x, then you will get in terms of the Hamiltonian, some function of Hamiltonian and beta will get if you just substitute. Right. This problem is similar to the previous one, but here we have different form of this Hamiltonian. So understood, right?
Yes, sir. Okay.
Okay. So we'll go to next question. Okay. So in this question we are asked the above question. Now s is plus or minus 1. Calculate the same variables for these parameters. So previously what we had, si equal to 0 or 1 we had. Now we have si equal to plus or minus 1. So for this case I will take first one is plus 1, second one is minus 1. So as s is plus or minus 1, what will be the values of m and n? Plus or minus 1, right? So I have the matrix element form for this Hamiltonian. Here for this Hamiltonian I have the matrix element form. Just I have to take different values for m and n for the next question. So in this question we were taking 0 and 1 for m and n value. Now we have to take 1 and minus 1. So let me rewrite this TMN form. This TMN form for our question. This is e to the beta j mn plus h over beta h over 2 m plus n. Now let's take this transfer matrix as 1 1 1 minus 1 minus 1 1 minus 1 minus 1. So for the first this is m and this is n value, right? First one is m value, second one is n value. So putting this value, we'll have first element as m is 1, n is 1. So this is 1 into 1 1. First one will survive, and here m is equal to 1, n equal to 1. So we'll have 2 in the numerator, 2 in the denominator will cancel. So effectively we'll have e to the power beta j plus beta h, right? Then for the second case, we have m value 1, n value minus 1. So for this case, 1 into minus 1 will be minus. So I will have minus beta j e to the power minus beta j. And for the second case, we will have m is 1, n is minus 1, so it is 0. So we won't have any contribution from the external magnetic field. So we will have only contribution from the spin interactions. Okay. So for the third element, we have minus 1 1. So similarly, minus 1 1 is minus, and the second term, this m plus 1 m plus n will be 0. So we will have e to the power minus beta j also here. So for the last term, we have m is minus 1, n is minus 1. So minus 1 minus 1 is plus 1. So we will have e to the power beta j, and then the second term, minus 1 is minus 2, and 2 will cancel, and 1 minus n will come here. So beta j minus beta h. So I calculated the transfer matrix as this. Now you can take e to the power beta j as x and e to the power beta h as y. Then you will have a matrix of the form xy minus of this is, so you will take this as minus. Okay, let's calculate this. So we will have, if I take e to the minus beta h as y, then what will be the value of e to the beta j beta h? So it's just minus, just like e to the beta h, which is, sorry, e to the minus beta h is 1 over beta h. So e to the beta h is 1 over e to the minus beta h. So which will be 1 over y or y inverse. So e to the beta h will be y inverse. If I am taking e to the minus beta h as y, if you take plus beta h as y, then you will have for minus beta h as y inverse. So it's up to you. If I take this plus beta h, then I will have xy here. This e to the this term plus this term, that means e to the power this into e to the power this. So I am taking x and y. So then e to the minus beta h will be y inverse. Here you will have y inverse. Here you will have x y inverse. So you have T matrix in terms of x and y. Then you can calculate the eigenvalues y1, lambda 1 and lambda 2 from this matrix, right? So now I am not going to do that anymore. You can calculate the eigenvalues, and from that you can calculate the partition function also. So after calculating the y1 and y2, you will have definitely some value will be greater than the other eigenvalue. So you take that bigger value, and in terms of n, in the limit of n very greater than 1, you take z as that lambda 1 to the power n. This is equivalent. You calculate this lambda 1 lambda 2 and calculate the partition function for this case also. Okay. Yes, any question?
No, sir. It's clear.
Okay. Okay, then coming to the next question, we are asked in question number 8, calculate the mean field Hamiltonian. So for calculating mean field Hamiltonian, so from class you might be remembering, for calculating the for simplicity, for Ising model. Okay, so it is easy for Hamiltonian like this, minus a si plus 1. For if we have Hamiltonian like this, it is easy to calculate the variables, partition functions, etc. very easily. This J is interaction between the adjacent particles. Right, this is the interaction strength. If we consider as it is spin, this is the spin-spin interaction strength. So it is without external magnetic field. This is calculation of this is very simple. Now if we are applying external magnetic field small h to the system, then we will have some extra contribution as h some summation of s over s as s. So if we apply external magnetic field, we will have some additional interaction term of magnetic field with the spin of the particle, right? So initially we had this kind of system, so it was easy to calculate the variables. Now we have external magnetic field, so the Hamiltonian is changed now to this. Now it's hard to calculate the variables from this kind of Hamiltonian. So we took some approximation, like we assume that this there is a effective magnetic field, and which is applied now, and we are assuming there is no interaction between the adjacent particles. There is no spin-spin interaction between the adjacent particles. It is replaced by the effective external magnetic field. So in that case, we can write this Hamiltonian as h is equal to h effective summation over I si. So initially, for simple case, you can imagine the interaction between the spin and of adjacent particles. So it was very simple case. Now if we are applying external magnetic field, there is a extra term of interaction of this spin with the external magnetic field. So for this kind of Hamiltonian, it is not very easy to solve in Ising model. So what we did, we are assuming there is a effective magnetic field, for which we are considering that this there is no interaction between spin. There is only effective magnetic field which is interacting with the spin states. So from this we can calculate the effective externally effective magnetic field, which will give me the same Hamiltonian, right? I just replace this kind of system with a different assumption like this, which will also give me the same Hamiltonian, right? So for this case, it is very simplified for us now, so it will be very easy to solve now. we can calculate this minus H effective as this del H over del Sk this is expectation value. Am I writing this correctly? You can check this from class. Sir has written this. Yeah, that's correct. So now we can calculate this effective H by differentiating our Hamiltonian with respect to the speed, right? So we are asked in question number 8, calculate the mean field Hamiltonian. So let's go to question number 8. Okay, we have a Hamiltonian like this. Okay, we just write this Hamiltonian. H is e to the power minus j summation over I or j, whatever, sj plus 1 minus or plus, maybe plus just check, plus h summation over j s. Just you can come. Okay, yeah, correct. Okay, we have a Hamiltonian like this. Now I have to find the effective external applied field. So for that I have to differentiate this H in with respect to Sk. So this value will be okay, H is not e to the power, it's just minus j summation over I j from 1 to n and h 1 to n. This is h value, right? Now I have to differentiate with respect to Sk. So for the first term you have Sj to Sj plus 1 summation over j to n. So first we are doing derivative with respect to Sk. So as j is dummy variable, I just replace this j as k in every term, right? Then the differentiation will be summation over k equal to 1 to n. I did the differentiation with sk, then only sk plus 1 will remain. So there are two terms, sk and sk plus 1. So I did differentiation for the first term. Now I can do one thing, I can interchange sk and sk plus 1. So as they are dummy indices, it won't affect much. So from that I will have one more contribution, as I will take this sk to the left hand side and sk to the right hand side. Then I will have again this sk plus 1, k equal to 1 to n, right? So I will have how much? 2 summation over k equal to 1 to n sk plus 1, right? So effectively I can write this as 2 some expectation value of sk As there are dummy indices, I can shift to k equal to 0, then this will be sk, k going from 0 to n. Now I am just rewriting this summation as this expectation value of 2sk. So this is from only the first term. Now coming to the second term, I have h summation over sj, j equal to 1 to n. Now I have to differentiate with respect to sk. So it is independent, h is independent of sk, I can take out. Now as j is dummy index, I can rewrite as k, then I'll differentiate it, then this will be summation over k from 1 to n, and this will be 1, right? Yeah. So effectively I'll have h here, and the summation will give some number, so which is a constant, just I am ignoring for the time. Now this minus h effective is differentiation of, as I am differentiating and then I am taking expectation, for that reason I took this expectation values here and here. So I just calculated the differentiation. I just now I have to put it. What will I have? H, and from the first term I had minus here. I just didn't take here minus, so let me take minus. Then I'll have minus 2, okay. So I got this effective magnetic field as h minus 2 sk, right? Now I have written my Hamiltonian as minus h effective summation over sj. Then I calculated this h effective value. Now I have to just put it in the Hamiltonian. So what is the Hamiltonian now? The minus h effective and summation over si. H effective I calculated minus h effective, which is h minus 2 sk, which will be multiplied with this summation value I right. So this is the mean field Hamiltonian, right? You understood, right?
Yes, sir. Noted.
Okay. Then we will go to next question. So in the next question we are asked to find the transcendental equation of this mean field solution Si. So previously we calculated the Hamiltonian as this. Now we have to find a solution for sk, this mean field sk, or Si, whatever. So for that we can calculate, we have Hamiltonian now in terms of this sk, or I can rewrite it as si. This is dummy variable si, so it doesn't matter. So I have h as small h minus 2 okay, here I forgot to write like j, so it is j, so we have one j here, so this is minus 2 skj. Effectively I have this Hamiltonian, right? Now I have this Hamiltonian, then I can calculate the partition function as trace of e to the power minus beta h. I have h, then I can calculate the partition function from this beta value, right? So shared will be trace of e to the power minus beta h is 2h minus 2j s, so this is si, right? And this is multiplied with summation over, okay, let's write it k, then I say we got this right here, h we got this. Now I'm just substituting this h value in this trace, so this will be trace of e to the power minus beta, and this is h minus 2j k summation over I s, right? Now as I mentioned, e to the power summation over ai can be written as product of e to the power ai, right? So I can rewrite this trace as trace of summation over e to, sorry, this is product of e to the power minus beta, this whole term. Now this summation will not be there, it is replaced by this product, it's si, right? Now trace means addition, so this trace will be trace of any matrix can be written as summation of the eigenvalues, right? Now this trace will be replaced by summation, and there is a product already, and this is e to the power minus beta, this term is si. Now for this question I have, as it is referring to question number 8, I have maybe s equal to 0 and 1, so summation over ai is there, so I can okay, I can interchange this product and summation. This product will go out and summation e to the power minus beta is and si. So now I have si value 0 and 1, so first I will put si equal to 0, so for that case I will have this is product, not pi, this goes from I, so this summation I am putting for the s value first 0, so it will be 1, this e to the power 0 is 1. Now for the second case I will put si equal to 1, so it will be e to the power minus beta and the rest of the term, which is h minus 2j expectation of si, like this, something like this. So this product is from I equal to 1 to n, so effectively I can write this as 1 plus multiplication of n such terms, so I can write this as e to the power minus beta, this term whole to the power n, right? This is my partition function now. So we are asked, to calculate the mean field solution for SI. So from class can write this formula as expectation value of Sk can be written as 1 over n del over del beta H effective ln of Z. So Z I have calculated. Now I have to put it here and differentiate with respect to beta H effective. So 1 over n now del over del beta H effective ln of 1 plus e to the power minus beta this term. There is a n in this logarithm, so this n will go front, then this n can cancel. Now we have to just differentiate with respect to beta effective H. So this is, let me write this. So initially we calculated the partition function from trace of e to the power minus beta H. So now H is my effective external field and summation over is spins, right? So we solve this to find this. So they are equivalent, right? I can write this like this or like this. So as I am going to differentiate with respect to H effective, let me write this as H effective summation over SI, right? H was minus H effective summation over SI. So one minus is here, already one minus was there, so it is plus beta. Let me write this clearly, e to the power beta H effective summation over SI. Now this differentiation will be differentiation with respect to ln will give me 1 over 1 of that factor e to the power beta this term, and with respect to beta H I am differentiating, so it should give me summation over this SI is there. So SI now goes from 0 and 1. So there are two values only. So if I do this summation, this will be 0 plus 1, right? So effectively I have 1 over 1 plus e to the power beta, and I can rewrite this H effective as H minus this what was this 2j this SK, right? Let's check whether we have answer like this or not. We have 1 over, yeah, here this is the answer. So in class you might be remembering sir has calculated this SK from this formula, and he got one transcendental equation, like he got some 10 hyperbolic in terms of beta and some SK, right? And then he plotted this in terms of SK like this, some function we got. So for our case, our Hamiltonian is different, our partition function will be different, so our transcendental equation is also different. So this SK we are getting like this for our Hamiltonian. right? You understood, right? I just did differentiation using the search formula that he introduced in his class. So in this question we are asked to calculate the transcendental equation. So sir got some transcendental equation in terms of 10 hyperbolic for his Hamiltonian. So for our case we have different Hamiltonian. The process is same. He also did took H effective, then he calculated the transcendental formula in terms of this. He got in terms of this 10 hyperbolic scale like this. So for our case Hamiltonian is also different, so we got our transcendental equation like this. You can refer to the second or first lecture of his week 6. Is it clear?
Yes, sir.
Okay,
Yes,
so
sir.
so it's time now, so we'll meet in next class.
Thank you. Okay, sir. Thank you.
Yeah, bye bye.